All right, people, here we go. Part 6 of our summer intro, I guess, to AP Stats. So let's imagine we're going to do linear transformations on random variables. So here's the idea. We take a quiz and it's out of 10 points. All right, Mr. Reboff wants to make this out of 100. Okay, so I've got a couple ways to do it, right? I can multiply everybody's grade by 10. That'd be an easy way to do it. I could add 90 to every person's grade, right? That'd be another way to do it. You'd probably all appreciate the add 90, right? But let's say those are the two options. So let's see what happens to a distribution. Um, so um, what happens if we multiply or divide by a constant? So we'll start with the multiplying. So let's say my distribution looked like this. Okay, this is called a normal distribution. We'll talk about that later, or normalish shape, bell-shaped curve. So right now I got 0 to 10. I got mostly 4s and 5s and 6s, right? If I multiply everything by 10, what's going to happen? Well, the zeros stay zeros. The ones go to tens, right? The tens go to hundreds, right? So after this is not drawn to scale. So don't hate on me. Just kidding. So now it's going to look something like, wow, I didn't do a very good job. Hundreds over here. Boop. There we go. All right, so now my distribution looks like this. Well, what's changed? What has changed? Has the middle changed? We call this the mean, right? Has the mean changed? Yes, the mean is probably now 10 times bigger, right? If it was 5 before, now it's at 50, right? So this is the mean with the 10 times x, right? So the mean changes. What about the spread of the data? So if we look at this is I'll use the term standard deviation. All right, it's the average kind of expected deviation from the mean, right? So if that's the standard deviation, what happens to that standard deviation now? Right? Look at it now. Oh yeah, the standard deviation has gone up by the same amount, 10 times. If this was, let's say the standard deviation was 1.5 before, now it's 15, right? It's times 10. So multiplying or dividing by a constant is going to change. It will multiply or divide, because you can divide as well, both the mean of x and the standard deviation of x. Okay, so it affects both, right? We see that here. What if I added, right? So let's say I had the same distribution going from 0 to 10, right? The average was 5, let's say. Standard deviation was 1.5, right? So the average spread was 1.5. What happens if I added 90 to everything? This whole thing would shift up, right? And now, again, not drawn to scale, we'd be going from 90 to 100. So if I just added 90 to this, it becomes 90. If I add 90 to this, it becomes this. What has changed? Yeah, the mean has changed, right? The mean would now be 95, right? Has the spread changed? No, it hasn't, right? So adding or subtracting changes the mean, but not the standard deviation. Okay, so the mean is something we call center of a distribution. Standard deviation is a calculation of the spread of the data. Okay, so multiplying affects both center and spread. Adding or subtracting affects just center, not the spread of the data. Cool, cool. All right, now we're going to use that here. Oh, we're reviewing what we did last time. This is kind of nice. Connor's playing a carnival game that involves shooting 2 free throws. Table below displays the probability distribution of X, the number of shots that Connor makes in a set of 2 attempts. So he can make 0, 1, or 2 shots. Find the mean of X, or the expected value, and the standard deviation of it. All right, so remember last time, expected value. Again, this is on your green sheet. We talked about it last time. Discrete random variables, mean. There we go. Expected value is equal to the sum of the outcome times the probability of that outcome. So I take the outcome times the probability of the outcome and add those all together. Here's the standard deviation. We'll hit that up in a second. So my key for this one, or my way of thinking, is multiply down and then add across, right? So 0 times 0.18 plus 1 times 0.5 plus 2 times 0.32. I think that equals, I did it earlier, 1.14 points or baskets made or something like that. All right. Which should make sense, right? We're just a little bit to the side of 1. All right. Always make sure it makes sense. It tells you if you did something right or wrong. All right, so standard deviation is, and we're going to use this, so big square root of the sum of the difference between the outcome and the expected value, or mean, squared, times the probability of that outcome, right? So again, be able to, you don't have to memorize these. You're going to have this every year for every quiz, every test. You'll even have it on the final exam. You'll have it on the AP exam. This is from the AP exam. Okay, it'll be a white sheet of paper or it'll be on your computer. You'll click on something and it'll come up on the hybrid test. Okay, but you will have this available. Don't have to memorize it, but you do have to know how to use it. All right, so I'm going to do the mean. 1.14 minus 0 is the first outcome squared. And it doesn't matter. I know some of you are like, shouldn't it be 0 minus 1.14? It doesn't matter because I'm squaring it. It's going to end up being positive. Okay, times 0.18 plus. I'll do it for the second one. 1.14 minus 1 squared times 0.5. And then the last one, 1.14 minus 2 squared times its probability, 0.32. Boom. All right. So I plug that into my calculator. I think I get something like 0.69 points. Okay, so that means on average, he would score 1, a little bit more than 1, and then standard deviation would go about almost 1 shot in either direction, which makes sense, right? Most of his stuff's here, right? 1 standard deviation away from the mean will capture a good majority of the data, but not all of it, okay? For a normal distribution or normal-ish distribution. All right. If the game costs Connor $15 to play and he wins $10 per shot he makes, what are the mean and standard deviation of N, his net gain from playing the game? So what is his mean if it costs $10 per shot? He wins $10 per shot that he makes. So that's 10x, but it costs him $15. So the linear transformation would be 10x minus 15. So mean of 10x minus 15. Well, let's start with that. Mean. Does multiplying affect the mean? Yes, it does. Does adding or subtracting, in this case, subtract the mean? Yes, it affects the mean. So both of these are going to affect the mean. So all I have to do is do 10, plug in the mean, 1.14, minus 15, and this is dollars. I could put the dollars here. I could do it at the end. So 10 times this minus this is negative $3.60. Okay, so this is his net gain from playing the game. Each time he plays, he would be expected to lose $3.60. Okay, not a fair game, right? Or at least for him, it's if you're the carnival owner or whatever, you're crushing it. All right, what about the standard deviation of 10x minus 15? We have to remember standard deviation, spread. Does multiplying affect the spread? Yes, it does. Does adding or subtracting affect the spread? No, it does not, right? We can see that here. The spread does not change because of the adding or subtracting. So only this matters. Only this matters. Okay, this doesn't. Okay, so the standard deviation is just going to be 10 times 0.69. So $6.90 is the standard deviation. Okay, so on average, he loses this amount, but it's a pretty big standard deviation, right? If every single time he lost $3.60, nobody would play that game, right? Or he wouldn't play that game. But sometimes he wins, sometimes he loses, right? So sometimes he makes, you know, whatever, and he feels good about it. Then sometimes he loses. This is how gambling works. The casino always wins, but there's enough variation to make you feel like maybe you can win. Okay. Know that. All right. We learned something here. All right, based on part B, is the game fair? No. Fair would be the um, expected net gain would be equal to zero. If not, how would you change the cost to play so that the game is fair? Well, you would have to go the cost times 1.14, or the cost to play, let's see, this is the cost. There we go. So $10 times 1.14 minus the cost needs to equal zero, right? So it's expected wins. What do we call that? I don't know. Anyways, every time he plays, he would be expected to win 1140, but since it's costing him $15, he loses 360. So if the cost was 1140 to play, he would have a net gain of zero. So 1140 would be the fair price. All right, cool. All right, playing with random variables again. Now we're going to be adding or subtracting them. We'll have some examples down below. Adding random variables and subtracting random variables. And let's see if we know the mean and standard deviation. Really, I kind of like using examples, but we'll just jump in. The expected value, if we're adding two variables. So let's say, I don't know, my wife and I are in a hot dog eating contest, right? And we want to see total, if we were a couple and we were competing as a couple, how many we would eat. And on average, I eat 20 in 5 minutes or whatever, and she eats 10 in 5 minutes. Well, to find our expected combined, we would just add those together, right? So the expected combined amount would be my expected amount plus her expected amount. Okay. Kind of makes sense, right? If we're subtracting, if we're wondering, hey, how much does Mr. Rebuff beat Mrs. Rebuff by in the hot dog eating contest? We're not actually competitive eaters. I just want you to know. There's nothing wrong with it. Joey Chestnut is a hero of mine. If you don't know who Joey Chestnut is, look it up. Okay. San Jose State, Spartan Pride, yo. All right. So we would just subtract, right? On average, I eat 20. On average, she eats 10. So on average, I beat her by 10, right? So that's that. Those make sense. Those are super easy. I'm going to go over here. I'm going to change this, and it's probably changed on yours already because I'm going to make a note of that. I'm going to do standard deviation, even though we don't know a lot about that yet. We know it's a measure of how far things are spread from where the middle is, right? And this is assuming that the variables are independent. Then we have this, the standard deviation of x plus y is equal to, okay, so to figure out what our combined standard deviation would be, I take my standard deviation and square it, and then I add it to her standard deviation and square it. These are called variances. So we turn it into a variance. We turn this into a variance. We add them, and now we have the combined variance, but we don't want that. We want it in standard deviation. So we square root it to get it back down into standard deviation. Okay. So just know that there's a formula for that. I take my standard deviation, square it, add it to her standard deviation squared, and then we square root it. And that will give me the combined standard deviation. If we're subtracting things, if I'm finding the difference, here's the crazy thing. Are you ready? X minus y is equal to, see if you notice anything. What do you notice? You're going to think I made a mistake, but I didn't. Do you see it? Okay. It's the same. We still add. Okay. There's a reason for this mathematically. Okay. The important thing is that we still add. Let's say, for instance, that if we had the same standard deviation and we did this, right? I'd be finding how much I beat her by. I beat her by 10 hot dogs per on average, right? But if we had the same standard deviation and I subtracted here, right? If it was, 25 minus 25 is zero, square root of zero, that would mean I always beat her by 10 no matter what. And that doesn't make sense, right? Every once in a while, I might beat her by 12 or I might only beat her by 4, right? So we always add there. So we can get into the math behind it if you want to, or you could research that on your own, have fun. But that is the rule. We always add, always add. Okay, so two random variables, x and y, independent with mean of x is 6 and mean of y is 8. Standard deviation of x is 0.5, standard deviation of y is 0.6. Find the mean and standard deviation of 2 times x plus 3 times y. They're jumping, double jumping, because not only are we doing this, but we're also multiplying it together. Okay, so we're just jumping in full bore here. So mean of 2x plus 3y is equal to expected value of 2 times x plus expected value of 3 times y, I think it was, yes. And that equals 2 times 6 plus 3 times 8, right? So we're going to double this, we're going to triple this, we're going to add them together, and we get 36. So the expected combined 2x plus 3y would be 36. Okay? This is kind of like if you got, if on average I make, or Steph Curry makes 6 2-pointers and 8 3-pointers in a game, what would be his expected point total, right? So he'd have 6 2-pointers, 8 3-pointers, and that would total 36 points. Kind of the idea here, if you need kind of an idea. For the standard deviation, though, standard deviation of 2x plus 3y, we're multiplying and adding. So we're going to kind of use this combined with the multiplying. So it's going to look something like this. So we're going to go the standard deviation, if we multiply, multiplying counts, right? So we would do 2 times the standard deviation of x. But this says that we need to then square it and then add it to the other one, and that's 3 times that standard deviation, 3 times the standard deviation of y squared, right? And then I add them up, and then I square root them, and that will give me the combined and transformed standard deviation. So if we look at it, we've got 2 times 0.5, and we're going to square that plus, and then here we have 3 times 0.6. Should have put a 0 in front. 3 times 0.6 squared. And we plug that into our calculator and we get, I believe, 2.059, right? So that would be Steph Curry, averages 36 points a night and his standard deviation is 2. So we wouldn't be too surprised if he got between 34 and 38. That's probably pretty low, right? Standard deviation is probably a little higher than that for Steph. Cool. Additional practice. Here we go. All right, let's go. This one has some cool stuff. Again, additional practice. Do this when you want. Okay. Let's see. The first one, 2 independent observations are made such that we consider the sum of these random variables a equals x plus x. This won't be a equals 2x because each one of these are random. They could be different numbers. We're going to do 2x over here. We're going to take one random number and multiply it by 2. Okay, so there's a difference between these two. We're going to show why this is different from this. Okay, that's the whole idea of this additional practice. Because these are independent, they could end up being different numbers, right? Because they have this distribution. On average, they hit 14, but there is a standard deviation of 2. So this could be 12, this could be, 15.2, right? They could end up being different numbers. For here, if x is, 15.2, we're multiplying that by 2, and we're going to get 30.4. Okay, so different problems. All right, so here we go. Mean of x plus x is equal to mean of x plus the mean of x, right? So the mean of x plus the mean of x. So we get 14 plus 14. So on average, it's going to be 28, whatever units that is. All right, the standard deviation of x plus x is going to be equal to the square root of standard deviation of x squared plus the standard deviation of x squared. That gives us, let's see, what is the standard deviation? Standard deviation is 2, so we're going to do root 4 plus 4, which is root 8, which is 2 root 2, which is somewhere around 2.8-ish, okay? So there's our standard deviation. All right, If we randomly multiplied the variable x by 2, right? So instead of adding it to another random variable, we do this. We'd have the mean of 2x equals 2 times the mean of x, which is 2 times 14, which is 28. So still the same center here, still the same mean, but watch what happens to standard deviation. It's going to be a little different. So standard deviation of 2x is going to be equal to just 2 times the standard deviation of x, right? So that's 2 times 2, which is 4. We're going to have more variability here, right, than we would here. Interesting, right? Interesting. Let's see. Discuss any, let's see, is it the same as, no, they are not the same. Not same. Is the random variable A the same as the random variable B? Not same. The mean is, but the standard deviation is different. Discuss any similarities and any differences you see with their means and standard deviation. Well, I already just said the means are the same. Standard deviation of B is greater than the standard deviation of A. Okay, I want to explicitly compare. The means are the same, but standard deviation of B is greater than the standard deviation of A. That's it. We did it. Fun stuff. All right. We'll see you on the next video.